Next slide. After looking at what went wrong on Venus and Mars, let's take a look at our home planet Earth. Earth has just the right temperatures and air pressure for liquid water to exist on the surface. Earth is unique in this respect. The oceans of water cover about 75% of the surface. The liquid water makes it possible for life to exist. Another unique thing about the Earth. Next slide. The Earth rotates once every 24 hours. Here it is about half a turn later, and we see our home in Kern County. Our atmosphere is unique because of the presence of free molecular oxygen. This oxygen supply would soon disappear if it was not continually regenerated by the photosynthesis process of plants. Soon disappear means within a few thousand years, which is geologically speaking a very short time. Plants take in water and carbon dioxide and the energy of sunlight. They turn it into carbohydrates and molecular oxygen, which is released as waste into the air. Next slide. Plants need liquid water, not ice, to live. Earth has a small greenhouse effect to keep the oceans from freezing. The liquid water also keeps the carbon dioxide from accumulating too much in the air. The carbon dioxide dissolves in the liquid water and is turned into limestone at the ocean floor. The photosynthesis of plants also helps remove carbon dioxide from the air. Next slide. Earth's climate has been remarkably stable for billions of years, avoiding the extremes of Venus and Mars because of the carbon dioxide cycle illustrated here. All the arrows going up to the air describe how carbon dioxide is released into the atmosphere to prevent us from becoming like Mars. And all the arrows going down describe how carbon dioxide is removed from the atmosphere to prevent us from becoming like Venus. All of this is pretty well balanced. Recall that carbon dioxide dissolves in liquid water, not ice. Our ocean water has been soaking up a large chunk of the extra carbon dioxide we've produced for the past decades, but it is beginning to saturate. Earth is unique in that its lithosphere is broken up into chunks called plates, and these plates jostle about because of the convection motion of the mantle below the crust. Among other things plate tectonics does in keeping our planet habitable, plate tectonics plays a key role in regulating the amount of carbon dioxide in the Earth's atmosphere. Carbon dioxide in the atmosphere dissolves in rainwater. The slightly acidic rainwater erodes land rocks, and the broken down minerals are carried to the oceans via the runoff. Calcium in the broken down minerals combines with the dissolved carbon dioxide in the oceans to create carbonates, such as limestone at the ocean floor. Through plate tectonics, the limestone and other carbonate minerals are carried to subduction zones where they are melted. The melted rock releases carbon dioxide through volcanoes. Volcanoes are the major natural, non-human, way that carbon dioxide is released back into the atmosphere over tens of millions of years of time. In the short term, they are just 1/100th of the human annual contribution. The formation of the limestone happens most easily in shallow, warm water. On Earth, the presence of continents makes it possible for places of shallow water to exist. The continents are created from lower density material than oceanic plates through the subduction process of plate tectonics. Liquid water plays a key role in helping the subduction process of plate tectonics to work by lowering the melting point of the oceanic crust and keeping the lithosphere pliable enough to bend and descend far enough into the mantle to melt. In turn, the temperature regulation of plate tectonics enables liquid water to remain on the surface. The temperature regulation happens because of a negative feedback process that cools the Earth if it gets too hot and warms the Earth if it gets too cool. A negative feedback loop works to dampen or reduce any change. That is, it tries to restore things back to the original condition. In this way, Earth has a thermostat that prevents temperature extremes described in this flowchart. The rate that carbon dioxide is removed from the atmosphere depends on the temperature such that the higher the temperature, the higher the rate that carbon dioxide is removed. If the Earth warms up, there will be more evaporation and rainfall, resulting in greater removal of atmospheric carbon dioxide. The reduced atmospheric carbon dioxide leads to a weakened greenhouse effect that counteracts the initial warming and cools the Earth back down. If the Earth cools off, the rainfall decreases, resulting in less removal of atmospheric carbon dioxide. The atmospheric carbon dioxide level will build back up because of the outgassing of volcanoes. A strengthened greenhouse effect counteracts the initial cooling and heats the Earth back up. This thermostat takes at least 500,000 years to adjust the temperature, so we cannot look to it to solve the short-term changes to the global climate. The thermostat did not work as well before about 540 million years ago. Earth had particularly long and deep ice ages, 750 to 580 million years ago, with glaciers reaching all the way to the equator. This graphic describes how Earth swung between these Snowball Earth deep ice ages and the hothouse Earth phases when all of the ice, even at the poles, was melted. Ice reflects 90% of the sunlight that hits it, while liquid water reflects just 5% of the sunlight, absorbing the other 95%. Increased ice makes a positive feedback loop that cooled the planet. Frozen water does not remove carbon dioxide. Liquid water does that. So the carbon dioxide from the volcanoes built up in the atmosphere. The geological record shows that the long snowball Earths alternated with episodes of extreme warmth, hothouse Earths, that melted all of the ice. The carbon cycle thermostat would have then worked to bring the temperatures to more moderate levels. Interestingly, it may be the presence of multicellular life, particularly worms, that has prevented the large temperature swings from happening again. Worms in the ocean sediments wiggling about prevent the methane and carbon dioxide from getting locked away and bringing on too large a drop in the greenhouse effect. Complex multicellular life did not evolve until about 540 million years ago, after the last Snowball Earth hothouse Earth swing. Even considering the Snowball Earth hothouse Earth swings, Earth's climate has been remarkably stable for billions of years, avoiding the much larger extremes of Venus and Mars because of the carbon dioxide cycle thermostat. There is the equivalent of 35 to 50 entire atmospheres worth of carbon dioxide locked up in the Earth's rocks as carbonates, mostly limestone. The contribution of carbon dioxide from the burning of fossil fuels by humans is a new input into this cycle with uncertain consequences. I know that I'm getting into a politically controversial area, especially here in Kern County, where a good chunk of our economy is derived from the extraction of fossil fuels, oil and natural gas. In the following stuff, I'm going to stick to what is known and how we know it. Since carbon dioxide levels have changed up and down many times in the past million years, at least, with the waxing and waning of the ice ages, how do we know that the current increase in carbon dioxide is not just a natural process? How do we know that the increase in carbon dioxide is due to fossil fuel burning? The top graph shows the recent carbon dioxide increase measured from the north and south hemispheres. The light green curve shows the data collected by Charles Keeling and others at the Mauna Loa Observatory in Hawaii. The dark green is from the South Pole Observatory. The wiggles up and down are due to the increase of photosynthesis in the spring and summer and decrease in the fall and winter. The northern hemisphere has more land, more photosynthesizing plants, so the wiggles are more pronounced. If fossil fuel burning is producing the extra carbon dioxide, we should see a decrease in the amount of oxygen. That is shown in the light blue and dark blue wiggles for locations in the north hemisphere and south hemisphere. Note that the scale for the oxygen plot has been magnified to make it more easily visible. The bottom graph shows the reduction, more negative, of measured carbon-13 to carbon-12 isotope ratio, as only happens with fossil fuel burning. This is the chemical signature of fossil fuel burning. Biochemical reactions have a preference for carbon-12, so biologically produced materials will be enriched in carbon-12, or proportionally reduced in carbon-13, compared to the carbon in inorganic materials. The two graphs also show the growing separation between the North and South hemispheres, since the industrialized countries in the Northern Hemisphere produce most of the fossil fuel carbon dioxide emissions. There are other pieces of evidence that corroborate the conclusion that the current increase in carbon dioxide is due to fossil fuel burning. See the links in the textbook to see them, but the two I've outlined here are the most important ones, with the changing carbon isotope ratio providing the chemical smoking gun, as it were. Could this artificial input into the carbon cycle upset the natural balance and create a runaway greenhouse effect like that on Venus? Maybe. How much would it take to tip the balance? We do not know. We are in the midst of a great planetary experiment. Current estimates of the amount of carbon dioxide locked up in fossil fuels say that it is highly unlikely that burning all of the fossil fuels will create a runaway greenhouse effect. As mentioned before, carbon dioxide levels and global temperatures many millions of years ago have sometimes been much higher than what they are today. However, while life in general and the Earth will survive just fine regardless of whatever amount of warming we cause, the particular form of life known as human, Homo sapiens, requires cooler temperatures to be comfortable or even survive. Furthermore, it does not take a large change in the global average temperature to create huge stresses that could threaten the survival of human civilization. To put things into perspective on how much difference just a few degrees change in the global average temperature can make, look at the global average temperature of the past several 100,000 years. Approximately 6 degrees Celsius in the global average temperature separates the pleasant environment today from the last ice age, when there were ice sheets over a kilometer thick covering a lot of our land. If you zoom in on the past 120,000 years, you will notice that the global temperature has been remarkably stable for a stretch of time longer than the other interglacials, about 11,570 years. Art and culture are about 30,000 years old, but agriculture and settlements, societies, did not exist until about 10,000 years ago. Agriculture and complex societies seem to take about 1,000 years of climate stability and a stabilized sea level to get organized. Archaeology has shown that minor climate changes have resulted in significant social disruption in great civilizations of the past, which may have implications for us in how we deal with climate change in the future. The prehistoric climate records show that carbon dioxide levels have tracked the temperature changes very closely, but there is some controversy about what causes what. Did temperature change before carbon dioxide levels? Or was it the other way around? Because the age determinations of the components in the ice core data cannot be made with sufficient resolution to definitively determine what came first. The climate feedback processes discussed in the previous class can make a cause-effect relationship between carbon dioxide and temperature in the past tricky to establish. Past climate changes, such as ice ages and interglacials, have been triggered by changes in the Earth's axis tilt and orbit shape. In those cases, carbon dioxide, water vapor, methane, greenhouse effect, and albedo changes have acted as feedback agents to enhance the effect of the axis tilt orbit changes. Although the prehistoric climate records may show that greenhouse gas levels may have lagged behind temperature changes, the physics of the greenhouse effect has been well understood for well over a century now, so we do know what an increase in atmospheric carbon dioxide can do. Now we are adding carbon dioxide independently of any natural temperature changes, and that extra carbon dioxide will be the triggering, forcing agent to a change in the global temperature via the well-understood greenhouse effect. We do know that the amount contributed by human activity has had an effect that is long-lasting because of the long time it takes for the extra carbon dioxide input to be absorbed back into the soil and rocks. The increase has happened in a very short timescale compared to past natural fluctuations in the carbon dioxide levels. Particular forms of life require much longer timescales to adapt to changes in global climate than what will occur with the rapid increase in the carbon dioxide levels. Therefore, the mix of species of life will undergo drastic changes in the next century or so. Human societies will need to adjust to those changes along with the changes of where food can be grown and changes in levels of available fresh water. Now to tell you about the International Climate Science Organization that has been in the news, the IPCC, which stands for Intergovernmental Panel on Climate Change. The Intergovernmental Panel on Climate Change, IPCC, is a review organization peopled by several hundred governmental and academic scientists from around the world. It publishes assessment reports every 6 or so years based on peer-reviewed literature. The IPCC does not do the climate research itself as an organization. It uses the results from the peer-reviewed research. The conclusions in the reports have to be agreed upon by politicians in all the countries before they are published, and that includes the US. So they tend to get watered down from the stronger conclusions from the scientists. Climate studies have hundreds to thousands of measurements all over the globe to look at averages. Remember the difference between weather and climate. Earth-observing science satellites have increased the number of measurements to many millions. Any data set will have some scatter about the mean, the average, so you are bound to find some examples that are less than the observed average trend. You cannot cherry-pick your data. Honest work includes them all. All of the relevant physics and chemistry and ever-expanding and increasing resolution data sets of land, oceans, atmosphere, and ice are programmed into supercomputer simulations. The computer models continue to improve as the hardware increases in power, and our understanding of the various feedback mechanisms improves. The computer models are checked and rechecked against the observed climate of the past 100 or so years. This graphic from the IPCC Working Group 1's most recent report in 2013 summarizes what the various climate studies have found. The next report will be released in 2021. The temperature changes are the beige panels, the ocean heat content are the light blue panels, and the polar ice coverage are the white panels. The observations are the black lines in the panels. The blue bands are the 95% confidence levels of multiple computer models that include just the natural agents of solar activity and volcanoes. The pink bands are the 95% confidence levels of multiple computer models that also include the contribution of human emission of greenhouse gases. Only the pink bands fit the observations. In trying to explain the warming that has already happened, climate computer models of different research groups using different inputs have found that the human factor must be included. The computer models that include just the natural agents of change, like the sun and volcanoes, show that the average temperature of the world and individual continents should have been stable, unchanged since at least 1900. The blue bands are flat. There is a gap between the black line observations and the blue bands that continues to grow. Once a climate simulation model has been validated against the climate conditions in the past, that is, reproduce the climate conditions we know existed in the past 100 or more years, they are used to make predictions of what will happen in the future, assuming various scenarios such as We either continue at the present rate of carbon dioxide emission, the rate of carbon dioxide emitted by humans continues to accelerate at the current observed acceleration, something in between, or we transition to non-fossil fuel energy production. So, the overwhelming consensus of the scientific community who actually do climate research, that is, those who are actively engaged in climate research, publish their results in peer-reviewed journals, and allow their conclusions to be tested by others, is that the global warming that is happening is mostly human-caused by the burning of fossil fuels. Any increase in solar luminosity has a much smaller effect on the climate. As a measure of the certainty of this, major insurance companies take the IPCC's conclusions into account in creating their business projections. Insurance companies know very well how to make money on projections of real future events, and they are not going to be swayed by any so-called environmentalist propaganda. If the science conclusions are good enough for the insurance companies, then you may want to think twice, three times, many times before discounting the IPCC conclusions. Even the US Department of Defense recognizes that climate change is happening and that it will bring stresses on food and water supply systems. I created a short summary of all this that fits on a single double-sided sheet of paper and posted it on the class Canvas and the Astronomy Notes website. Also on the Astronomy Notes website is a page that answers all the objections of the global warming skeptics. So check it out.